Hello everybody, it's Mr. Canfield in for another lesson. Today's lesson is antidifferentiation, also known as integrals. So that's where we're starting today. We've done some of this, we've basically done everything that we're going to see today, but in reverse. So the big question you're going to ask yourself in general, if we're ever trying to take an integral or an antiderivative, because they're the same thing, is you just want to ask yourself, what did I take the derivative of to get what I see? So, you know, if we took the derivative of, what did I take the derivative of to get 2x? Well, let's see. I know that the power used to be 1 greater, so x squared. And then, well, if I think about that, if I take the derivative of this, the 2 comes out front. There you go. Similarly, if I look at this one, 7x to the 6th, well, the power would get raised by 1, x to the 7th, and then the 7 is going to come out front, so perfect. And then this one, let's see, well, if I took the derivative of sine, I would get cosine. So the thing is, these are all an antiderivative of what we see. If we want to get the antiderivative, we need to tack on a number. The thing is, I could tack on any number, and so we put a c here to represent any number. So we call this our constant of integration. And the big deal with that is whenever we're taking what we call an indefinite integral, whenever we're taking an integral, an antiderivative, we're going to tack that c on saying, hey, any number could have been there. Like this could have been x squared plus 53. Because when I take that derivative, the derivative of the constant goes away. It's just 0. So that's why we have that c on there. C is considered arbitrary. It really could be any number. All right. So let's see. There's this whole family of functions, of equations, sorry. This family is called differential equations. Notice how each of these has a derivative in it, dy dx or y prime. We're going to study this later on in the school year, but the idea is we could find a solution to these by taking the antiderivative and getting y. So in this case, the antiderivative would be y is equal to x squared, but there's a 3 there. So like if I had the 3 here, that when I take that derivative, I get 6. So I would need to then divide it by 2. So I could say y is 3x squared over 2 plus c. There's some constant there. This is called the general solution. We're going to find what we call a particular solution later on. We can do the same thing with this. The real official way that we do it is we multiply both sides by dx. We get dy is equal to 6x squared minus 2x plus 3 dx, and then we integrate both sides. This is like the real way that we do this. And the integral of 1 dy, well, there would need to have been a y there. And yes, there could be a plus c as well. We could call that c1. And then over here, if we take this antiderivative, let's see. And I'm going to go into more detail about how I get these so quickly. Well, let's see, it's going to be x cubed, and there would need to be a 2 here to turn it into 6 when we're done. Okay. Then here it's going to be minus x squared, and then here it's going to be plus 3x, and then there's going to be a plus c. It's a different c, though. There's a constant on both sides. That's kind of weird. And so in general, what we're going to do, instead of putting plus c on both sides, we're going to collect them over here. And so instead of saying y is equal to 2x cubed minus x squared plus 3x plus c2 minus c1, c2 minus c1 is just another number. Number. So instead of doing that, we just put a single c. So we kind of bypass that whole switching around, and then that's all we got to do. Then we get over here, and we have y's and x's on the same side, and stuff starts to break down. So a big thing I wanted to talk about here was that we're going to be using antiderivatives to find what we call general solutions, but they're very complicated ones. There's this whole course called differential equations that just focuses on different things related to differential equations. So if we wanted to find the general solution of this one, Well, we'd multiply both sides by dx. We'd get dy is equal to 2dx, and we'd integrate both sides. I might have glossed over this a little bit too fast earlier. That says dy, that says dx. This is called the index of integration, and it's telling us the letter we care about. That's why the integral over here is y, because of the dy, and why the integral over here is 2x. So, yeah. Now if you ever kind of skip this middle step here and like you just show me this and you're like y is equal to x to the 5th plus c, I'm fine with that. That's simple enough. We're gonna get into really complicated examples later that are not that simple. But like I said, anti-differentiation is also known as taking the integral. And you always need this sandwich. You need the left side of your integral sandwich and the right side of your integral sandwich. So this is our integral symbol, or if anti-differentiation symbol. We call this the integrand. And then this is our index. Without these things, you can't take an integral. So this question down here is an interesting thing worth thinking about. What happens if you take the antiderivative of something and then take the derivative of the answer? So of this 5x to the 4th, if we took the antiderivative, we would get x to the 5th plus c. So what would happen if we took the derivative of this? We get 5x to the 4th plus 0. Oh, we'd get what we started with. It's because integrating or anti-deriving and deriving, differentiating, they're opposites or inverse operations of each other. All right, so let's look at some basics. So we know the derivative of a constant is 0. Then that means that if we were to integrate 0, we would get a constant. We know that the derivative of some constant times x is just that constant. Therefore, if we just integrate some constant, just go backwards. These are all going backwards. Then we know that that is just kx plus c. So similarly, now this is where it starts to get a little bit messy. X to the n, well, we know we're going to multiply the front by n, x to the n minus 1. Notice how I multiplied, then subtracted. Multiply, then subtract. The way that we do this is we reverse and reverse. So we unsubtract first, which means we're going to add first, and then we're going to unmultiply second, which means we're going to divide. So I'm going to add 1 to the exponent, and then I'm going to divide by my new exponent. In the same way that the derivative of a constant times a function is the same as the constant times the derivative. Another way to put that is, if there's a constant times stuff, just take the derivative, ignore the constant, leave it there. This works the same in integrals. We can actually bring it out front and then integrate. And the fun part about this is the antiderivative or the integral of lowercase f of x a lot of times is written as capital F of x. We want to be careful about how we rearrange these letters because that's 3/4 of a really bad word. So let's keep going. If we look at this one, it just says take the derivative of a bunch of things added together. Then that's the same as all their derivatives added together. It works the same with the antiderivative. So again, using the uppercase notation to explain what we're doing. Oops. Now this will have a plus c on the end, and that c is going to be like the collection of all of those individual constants. We don't need to think about each one having its own constant. All right, so let's take some antiderivatives. Well, what did I take the derivative of to get 6? 6x. What did I take the derivative of to get 7x? 7x squared. Not quite, because the derivative of this is 14x. So I would then need to divide this by my new exponent. The derivative of that, well, I would have taken 8x, the derivative of 8x to get 8. And then on this, so what I do for these is instead of kind of thinking through it the way that I'm modeling, I really just go, okay, I've got a I've got a 1x cubed. I add 1, divide by the new one. Here I leave this alone. I add 1, divide by the new one. Here I leave this alone. I add 1, I divide by the new one. That's the way I actually do this. And I hope that you are frustratedly screaming at your computer screen or phone screen or wherever you're seeing this, going, Canfield, you did not put plus C on any of those. I actually did that on purpose. Generally, in class, when I forget, I actually forget, but because everybody forgets. We all forget the plus C every now and then. In terms of being correct, it's a huge difference. In terms of points that I'll give you on a test or quiz, it's not a big difference. As important as it is, and as necessary as it is to write it, forgetting it is not the difference between passing and failing. Forgetting it's the difference between an A and a high A, or an A and a B, depending on how bad other things go. All right. The thing is, right now, the only thing we know how to do is to increment the power. We don't really have anything else. So like on this one, the only technique that we currently have is if I were to rewrite this as x to the negative 4 dx. Now that we have that, I can add 1 to the power and divide by my new power, and we'll have our antiderivative. Now, we're not supposed to leave negative exponents, so I'm going to bring it back down to the denominator, but similarly with this one, this is x to the 1/2. So notice how I'm leaving the integral and the index of integration until I actually take the antiderivative. So now I'll add 1 to that and get 3/2. And I need to divide by 3/2. That's kind of kooky. So instead of putting divide by 3/2, I actually like to just multiply by the reciprocal. I like to say 2/3 x to the 3/2 plus c. That's personally how I like to handle it. Saves me some writing, saves me some time. This next one, right now, the way that it looks, we don't really have a technique to handle that unless we alter how it looks. So I'm going to break the fraction up. And I'm going to think about this. Okay, this is really saying x to the 2 over x to the 1/2. Notice I still haven't taken the antiderivative yet. I haven't integrated this. So remember that when we divide exponents, we're really subtracting them. So 2 minus 1/2 is 1.5 or 3/2. So now I'm taking the integral of x to the 3/2. Oh, I can do that. Plus 4x to the negative 1/2 dx. This is now possible, thankfully. So now I'll take the antiderivative. I'll get x to the 5/2. And like I said, I like to multiply by the reciprocal. And I'm just going to leave that 4x to the 1/2 multiplied by the reciprocal. I just need a little bit of cleaning up. So I got my 2x to the 5/2 over 5 plus 8x to the 1/2 plus c. All right. So now we can get really messy things. But remember that this cube root of x to the 4th is really just x to the 4/3. So I'm just going to be subtracting each of these by 4/3 individually. Well, this is 12/3. This is 6/3, and this is 0/3. So I can rewrite this as the integral of 6x to the 8/3 minus 2x to the 2/3 plus 3x to the negative 4/3 dx. So now when I antiderive this, I'll have to add 3 over 3 to each of these, and so I'll get 6x to the 11/3 times 3 over 11 minus 2x to the 5/3, and then multiply that by 3 times 5. Plus 3x to the negative 1/3, and we'll be multiplying this by negative 3 over 1. And so we can clean that up if we want and get our 18/11 x to the 11/3 minus 6/5. Who made this problem? X to the 5/3 minus 9 over x to the 1/3 plus c. I wrote that super clean. It should be super easy to read. LOL, JK. All right, anyway, what about 1 over x dx? Well, if we think about this, this is the integral of x to the -1 dx. So if I add 1 to, I get x to the 0 over 0, which does not exist. Our pattern does not work here. And that's because you may or may not remember this. I may or may not have taught you this. The derivative of natural log of x is actually 1 over x. And so the answer to this is actually the natural log of the absolute value of x. And we'll talk more about the absolute value and why that is the case a little bit later. But this is a weird situation, more just to show us that we can't blindly follow patterns with these. We really do have to be thoughtful. I say that after I've blindly followed patterns for the whole page. Wonderful, inconsistent me. All right, let's see what's next. So this says find the particular solution for dy dx is equal to 3x squared minus 1 if f of 2 is equal to 4. And so all it's really saying is it's saying separate it out like you normally do, 3x squared minus 1 dx. Integrate both sides. So over here we get y, over here we get x cubed minus x plus c. And remember, this is called the general solution. So if I want the particular solution, that takes this into account. This says when I plug in 2 for x, I get 4 out for y. So I can literally do that. I can plug, so y is 4 when x is 2. And if I go through and just do the algebra there, I get 8 minus 2 plus c, so that's 6. Subtract the 6 from both sides, I get -2 is equal to c. And so my particular solution, is y is equal to x cubed minus x minus 2. So this solution has a derivative of that. Sorry, earthquake. This equation has, that is the derivative, and has that initial condition met. So, woo. Here's kind of a, I don't know, spiced up example. It says f double prime is equal to 2. F prime of 2 is equal to 5, and f of 2 is 10. Find the particular solution to the given second order differential equation. Ooh, second order differential equation, scary sounding. Second order just means 2 derivatives. So, check it out. We know f double prime of x is equal to 2. Well, then what does that mean that f prime of x is equal to? Take the antiderivative of that. It's equal to 2x, sort of. Right? If we take the derivative of that, we'll get that. The only thing is, I need to be a little bit more general, and I need to put a plus c there. And say that, okay, the antiderivative of f double prime of x is 2 is just f prime of x is equal to 2x plus c. There. But we also know something about this. We know that f prime of 2 is equal to 5. So that means that if I plug 2 in here, I get 5 out. So 5 is equal to 2 times 2 plus c. And I can solve this and find out that the c for this one is 1. So I can say, hey, f prime, I know that you are equal to 2x plus 1. And then I could integrate this and get, well, then that lets me say that f of x is equal to, well, let's see, I'll add 1 to the power, get x squared, and the 2 is going to go away, so x squared plus x plus c. And so all I've got to do now is find out what this c is. And some people, when they're doing these, they like to say, hey, that's C1, this is C2. It's a great way to remind ourselves that these are different. This is a very consistent way to do this. The way that I was just kind of leaving the number off of the C, it's a little bit more slapdash. Is that a phrase I'm allowed to use? It's a slipshod, is there? What's another one? Haphazard, unclear, unhelpful. Well, anyway, I got C2 is equal to 4. Yeah. So then that means that f of x, the particular solution, is equal to x squared plus x plus 4. And there you have it. So how many more slides do I have left? Cool. We got a few more. Should have enough time before I've got to get going. All right. What about trig? All right. So remember, the big idea here is we're just going backwards. So I know the derivative of sine is cosine. I know the derivative of cosine is negative sine. And the derivative of tangent is secant squared. I know the derivative of secant is secant tangent. And I know the derivative of cosecant is negative cosecant cotangent. And then the derivative of cotangent is negative cosecant squared. So if I know all those, then that means I know all of these antiderivatives as well. I know the integral of cosine is sine plus c. I know the integral of sine, ooh, careful here, is negative cosine plus c. I know the integral of secant squared is tangent. Notice how we don't actually know the integral of secant on its own. Nor do we know the integral of tangent on its own. Let's see, the integral of secant tangent, that was secant. This one's another negative one. This one was negative cosecant. And this one was negative cotangent. So you just have to know, what did I take the derivative of to get this as a result? And that's how you know what those are. Remembering that anything that starts with a C makes a negative pop out. I'm really happy that that happens, because that, I mean, the wording and language that we chose for these things, I'm sure we got that language before we started taking derivatives of it all. So I'm really happy that anything that starts with a C, when you take the derivative or antiderivative, the negative pops out. It makes life so much easier for memorizations. So these four, tangent, cotangent, secant, cosecant, we don't know those. Oh, if this was too fast, you have Google. You can look it up. Or, you can pause the video. So we do not know any of those. We have to wait, honestly, we have to wait till Calc 2 to, oh, sorry, no we don't. Sorry, I'm thinking of natural log. The integral of natural log is tough, but these, we're gonna have to wait until we learn how to handle like reverse quotient rule kind of things, reverse chain rules, the real one. But not now. All right. We do not know who has them, so for now we have to wait. But these are great. So let's see. The integral of 4 sine of x dx, that's the same as saying 4 integral sine x dx. And of course, the integral of sine is negative cosine, so this is negative 4 cosine x plus c. Sorry, I had to pause for a second. So there we go. This one, the way this looks right now, we don't have a way to handle that. We're going to need to change the way it looks. So I'm going to pull a 2 out front. That, I imagine, will be good. Then I can think about this as sine x over cosine x times cosine x. I'm doing this on purpose because I know what's going to happen. But like the idea, just like we had to do in pre-calc or in trig, was taking things like this and kind of breaking them apart and finding relationships. I know that sine over cosine is equal to tangent. I know that 1 over cosine is equal to secant. If you're not seeing it yet, let me just rearrange this. And so this is actually one of the most important things that we can pull from trig, this idea that we can rearrange stuff, we can rewrite things as different things that they equal. Because now we know this antiderivative. We know that the derivative of secant gets us secant tangent. So I can say this is 2 secant x plus c. So yeah, these get pretty messy. Now we have a good old one over here. There is a typo. This needs to say tangent squared x. All right, I don't like that negative that's in both of those. I'm going to pull that out front and say negative the integral of tangent squared x plus 1 dx. So I don't have a derivative that's equal to tangent squared. If I did, that'd be great, and I just plug that in and then say that's x. When I see the squared, that's a hint to me to use sine squared x plus cosine squared x is equal to 1. The Pythagorean identity. This almost always shows up somewhere in the AP test. So I need to see tangent though, and I don't see tangent. So I'm going to divide everything to make a tangent up here. I know that sine squared over cosine squared is tangent squared, so I'm just going to choose to divide everything by cosine squared. And we get tangent squared plus 1 is equal to secant squared. Oh, hey, look at that. Tangent squared plus 1 is secant squared. That means that we can just go in and replace it. So we'll just replace this with a secant squared then. So it says secant squared x dx. We can take the antiderivative of that and get tangent, right? So we can say negative tangent x plus c. So the ideas here aren't new. It's applying what we learned in trig, which for a lot of people feels really heavy. Practice is absolutely your friend in that. So now there's something called rectilinear motion. It's just standard moving particles. So like we're used to the vertical ball movement problems like below, but now it's backwards. So let's make up a planet. Let's call it Jattern. A ball is thrown upward in a vacuum. Acceleration is blah. If s, meaning position of 1, is 122, and velocity of 2 is 24, find the position of the ball at 1.5 seconds. So we know the acceleration, a of, there's no variable given. I'm going to use a of t because t generally stands for time, is equal to negative 60. Okay, so then if we integrate both sides with respect to time, then we can say that the velocity is the reverse of acceleration. If we think about that, if I take the derivative of velocity, I get acceleration. So this would need to be negative 60 t plus c. And we know that when I plug in 2 for t, I get 24 out in my velocity equation. So I can say, well, I get 24 out when I plug in 2 for time. That can help me solve for c. So I'm going to have to take my negative 120 and add 120 to both sides. I get c is equal to 144. And again, I'm being a little bit improper by not putting c1. So now I know that my velocity equation is equal to negative, good job me, negative 60t plus 144. Okay, so if I look at that, and we were to integrate both sides with respect to time, then we can see that the integral of velocity is, well, what did I take the derivative of to get velocity? Position. So we're going to say position of time is equal to negative 60t squared over 2 plus 144t plus c. All we have to do is integrate that. And I know s of 1 is 122, so when t is 1, oh, this I can cancel this and write 30 instead, can't I? So negative 30 times 1 plus 144 plus c. 122 is equal to negative 30 plus 144 what is that? 114 plus c. If I subtract the 114 from both sides, I get 8? 8. So c is equal to 8. I should be calling this c2. Be a little bit more proper. So that means my position function is negative 30t squared plus 144t plus 8. And so if I want to find the position at t equals 1.5, now I just plug that in. And I don't have my calculator on me right now, so we'll say it's equal to whatever number we get there. And I want to make sure that I use the appropriate units, so I go back and look in the problem and I see they use m for position. So all right, let's see what's next. I'm trying to be as brief as possible with this to get through it quickly enough. But I think, yeah, I need to get going. I'll do the last two at a later point in time. Hope this was helpful. Have a great day.